we're going to get into the WTF section. Okay, what the flux? And so a lot of what I do is actually, I do some pool work, I do some flux work. Many of you guys probably know that soil respiration is comprised of so many different respiratory processes. It's actually harder to study than photosynthesis, because photosynthesis is limited to fewer processes. When we measure the respiration coming out of soils, it's both autotrophic and heterotrophic. Okay, plants and microbes are both contributing to that CO2. But the thing is that these autotrophic and heterotrophic processes are probably responding to climate change differently, right? And so one of the things we've done a fair amount is to use stable isotopes to try to partition respiration into its more functional basic components, so we can answer the question, for example, how will warming affect decomposition rates? And so here's just a little diagram that sort of explains what I just said. There's autotrophs, there's heterotrophs that are both respiring. Yeah, you guys know that. And so this is a kind of busy diagram, but it just basically it's explaining a number of different soil respiration partitioning methods. Okay, there's a lot of different methods. Of course, we want the thing that's the most universal, that causes the least disturbance, but there is nothing up in that corner, right? We try to avoid this, most disturbance and least universality, right? And so C13 of free air CO2 enrichment is sort of in this less disturbance zone, sort of maybe medium universality, whereas root exclusion, where we just kill the plants, is in this higher disturbance but higher universality zone. Yeah?
Yeah, just because what exactly do you mean by disturbance? Do you mean the disturbance in the soil column, or is that what you're talking about?
Disturbance of the soil, disturbance of the whole ecosystem, disturbance of the microbial communities. So we just talked about the rhizosphere and the microbiome of the rhizosphere. What happens when we kill the soil, the plants? Right, so there's a lot of disturbance that's caused. Right, so I'm going to compare the C13 isotope partitioning with root exclusion partitioning of soil respiration, okay? And here's a project that we had going in Wyoming for about 8 years. We called it Face with a pH, the Prairie Heating and CO2 Enrichment Experiment. And it was a factorial with 2 levels of CO2, ambient and 600 ppm, and 2 levels of temperature, which was about 3 degrees increased, and it was replicated 5 times. And so I'm going to compare those 2 methods of respiration partitioning. Oh, and that's just a reminder that the tank gas that was used in the elevated CO2 portion of the experiment, there's 10 rings that had the elevated CO2, 5 at ambient temperature, 5 at elevated temperature, and it was that tank gas is about -39 per mil. And so when we mix -39 per mil, 200 ppm of that with 400 ppm of background air, we get about -20, if I remember right, per mil of the air on the elevated CO2 plots, compared to about -10 in the ambient CO2 plots for the CO2 C13. So this is just the flux rates from one growing season. And it's kind of crazy there, because there can be bimodal precipitation regimes. Grasslands are challenging to study sometimes because of that. And so we have this there was a significant interaction between the CO2 effect and time. So sometimes the elevated CO2 treatment had higher respiration rates, sometimes it had lower respiration rates. So it's kind of challenging to understand what's going on when you're looking at the total flux of soil respiration. And so all the background of what's going on there specifically is a little bit to the side of how the roots and microbes respond and how the partitioning was done. So this is a picture of how my Roundup plots look. Okay, I love Roundup. It does cause issues, but it's actually a pretty handy way to do root exclusion in grasslands. And so we have actually root barriers that don't allow roots to grow in from the sides. But how do you kill perennial grassland, right? Are you going to pull up all the grass? Well, that's going to cause a really big disturbance, right? So we just spray it with Roundup, come back a few weeks later, and guess what? There's like no root respiration. right? And so this was just like maybe a month after I sprayed. And this is the elevated CO2 at ambient temperature. This is elevated CO2 at warmed, higher temperature. And the SR is this total soil respiration. MR is just the microbial respiration, right? So on those Roundup plots, I'm just assuming that it's only microbes doing the work. And it's about half, right? Just from killing those plants, we reduce the respiration, the total respiration by about half. And we didn't really see much of a warming effect, right? If you sort of, close your eyes, you could sort of imagine that there's a similar amount of decomposition. So we can think of this microbial respiration as being decomposition, right? Similar amount coming out, whether it's warmed or ambient temperature, right? Here's a picture of how we're doing the isotopic mass balance partitioning. This is just we've got our new end member, or our root end member, the roots, and the microbial end member, and we do Keeling plots to get the soil respiration value. We collect the CO2 from the flux within chambers carefully without fractionating it or causing non-steady state issues. We determine not only the microbial and root end members, but also their variability, and we propagate the errors, okay? And so here's just a couple pictures of how some of those little pieces look. We do the roots really quickly because they actually do kind of change over time. And so we just do these little incubations in the field in our syringes, and then just save the CO2 into exotainer vials that have magnesium perchlorate in them, so they don't get too much messy water exchange going on. Tyler. And so here's how we estimate the end member of the microbial respiration. We do these long-term incubations. And so this is almost a year. This is just an example. And you can see that in all of our treatments, actually, we have this increase in the delta C13 with time. And in the non-elevated CO2 plus, we can see that it increases by, guess what? About 3 or 4 per mil. Cool. We can understand why that is, right? So here's the very beginning of the incubation, it's kind of looking like plant material. At the end of the incubation, it's looking more like older soil organic matter. And so that's what we use for the microbial respiration end member. You can see that there's some error bars involved here, all right? So we have to propagate those errors. And many of you guys have heard about Keeling plots. We'll learn more about that hopefully tomorrow from Dave Bowling. But when we put a chamber on top of the soil and we just keep it closed for a while, we can just watch the CO2 accumulating and then the delta C13 value decreasing, okay? Because the air is pretty much always higher in delta C13, higher delta C13 value than what's coming out. And so we basically just solve for the intercept, and that gives us the delta C13 of the mixture, the soil respiration that's mixed between the roots and the microbes. Okay, and so that's what I'm plotting here, the delta C13 of soil respiration in the elevated CO2 ambient temperature, elevated CO2 warmed plots. And so in the early April, and the red line is microbial and the green line is the root end member. Okay, so I just left the error bars out for simplicity. But before, in the early part of the growing season, the values, the soil respiration is close to the microbial end member because we hadn't turned on the tank gas yet. So so the root respiration hasn't been getting labeled yet. Once we turn the tank gas on, which is like middle of April, guess what? The delta C13 of soil respiration goes down a lot. And so what is the effect of warming on the partitioning of the soil respiration according to the isotopes? It's more microbial. What did you say, Tyler? It's more bacterial or more microbial, right? So using this method, we see that warming stimulates, so in other words, and we can tell that because the delta C13 of soil respiration is closer to the microbial end member in the warm plots than in the non-warm plots. Right? Can you guys see that? It's totally intuitive. You don't have to solve the mixing model. Right? Of course we do have to solve the mixing model, we do, but you can just look at the data, right? And so that's why, of course, us isotope geeks like to just look at the raw data. But then we sometimes make the mistake of thinking that, oh, everyone else is an isotope geek and all they want to see is the raw data. No. They want to see, the final result. They want to see the percentages, right? And so this is kind of the story, is that our two different partitioning methods tell contrasting stories. They have different results. Right? So root exclusion tells us that there's no effect of warming on decomposition. Right? So this is the decomposition rate, or the fraction from microbial. Right? But the isotopes tell us that there's much of a stimulation of decomposition by warming. Right? And so, may not be a Nature paper, right? It's kind of methody, but yeah. So which is the best method? Well, isotopes have less of a disturbance effect, right? So that fact that we're using a non-disturbing method might be telling us a little bit of a better, more natural result.
Isn't this kind of intuitive? Because in the root exclusion, you kill the roots, which is gonna so you didn't.
Well, so yeah, we're killing the roots, but we're measuring the soil organic matter decomposition only.
Yeah. So, but the root microbial connection and the root exclusion obviously could play into biogeochemistry.
Yeah, and so that's part of it. That is part of it, but it's actually really hard to. We actually need to apply a third isotope, like say radiocarbon, to see how much of the soil respiration is from the microbes next to the roots. Right, and people have done that, but not in the field.